All right, so we just talked about this idea that oxygen is primarily transported by being bound to hemoglobin, and that we've seen so far four different things that affect how much oxygen is bound to hemoglobin. So, quick recap. One thing is that as oxygen levels rise in the blood, oxygen will bind more to hemoglobin due to Le Chatelier's principle. As oxygen levels fall, hemoglobin unbinds from oxygen. That's one. A second one, we saw that if CO2 levels rise, hemoglobin is going to unbind from oxygen, which helps us deliver more oxygen to the tissues. That's two. As the blood or tissue gets more acidic, oxygen unbinds from hemoglobin. That's three. And finally, we saw that temperature as it increases also causes oxygen to unbind from hemoglobin. So that's four things so far. And all of those kind of indicate how much activity a muscle has: oxygen levels, temperature, pH, CO2. But it turns out there's a fifth factor that is unrelated to exercise, and it tends to usually have more to do, or one of the main ways that we end up producing it is if we ever go to high altitudes. Because at high altitudes, um, there's a lower total air pressure, and as a result, the partial pressure of oxygen is much lower. And so we feel short of breath because we're not breathing in as much oxygen. And so, what can we do about it? What we can do is start producing this molecule that we're just going to call 2,3-DPG. And what you notice is that when we start producing that molecule, that causes our hemoglobin curve to shift to the right, which means our oxygen is going to unbind from hemoglobin more likely, and that oxygen is going to be delivered to the tissues, which is great when we're at high altitude, because when we're at high altitude, we can't breathe in so much oxygen or as much as we'd like. So it'd be great if the oxygen we did have unbinds from hemoglobin so it can feed our tissues. So at high altitude, we produce this so that we'll release more oxygen at each tissue and help that tissue deal with being at higher altitudes. And this is actually one way that you kind of get used to being at higher altitudes. Is over the course of a few days, you start producing this molecule. You'll start releasing more oxygen from hemoglobin, so your tissues will be getting the oxygen they need. So usually you'll start seeing this molecule being produced if you go to high altitudes, or if for some reason you're anemic, where you're not getting enough oxygen for some other reason. Maybe you don't have enough red blood cells, or maybe you don't have heme groups or functional hemoglobin, and so the oxygen you do have, you want to make it available for your tissues. So that's all just oxygen transport by hemoglobin. But remember that we also need to transport CO2. Now we need to figure out how CO2 is transported. This one's not maybe as complicated in a way, and we've kind of seen already the primary way that oxygen is transported. Because if we look at this, what it's saying is that there are essentially three ways that CO2 can be transported. It can dissolve directly in the plasma, so you can see about 7% of the CO2 in your blood is just dissolved in the plasma. CO2 is much happier in watery substances than oxygen is, and so a more significant portion of the CO2 can just travel on its own in the plasma. But 93% of the CO2 is actually inside your red blood cells. Some of it binds directly to hemoglobin, just like oxygen does. But the great majority of CO2 is transported in your blood in the form of bicarbonate ions. So let's look at each of those two modes of CO2 transport. So just like oxygen, CO2 can bind to hemoglobin to make what's known as carbaminohemoglobin. You do not need to remember that. You just need to remember that this is CO2 bound to hemoglobin. And we know that this reaction is going to go to the right to make this if there's a high partial pressure of CO2. So that's one way I can transport CO2. The other way is that if CO2 comes into the blood, we can convert it into bicarbonate ions. So if you look at this bicarbonate ion, you can kind of see the CO2 hiding in there, right? CO3, there's a CO2 in there. So essentially what we did is took this CO2 and converted it into bicarbonate. And this is actually the main way that we transport CO2 in the blood, is in the form of bicarbonate. All right, so why are we talking about all these individual reactions and how you transport it and stuff? And the reason we're talking about that is because all of these things are occurring at the exact same time, and they're all kind of affecting each other. So I wanted to show you actually this picture in video form, and then I promise I will shut up and let you finish your weekend or let you go to sleep or whatever you are doing right now. So we're going to try to take all the chemical reactions we've talked about and put them all together. All right, so let's take a quick look at all of these reactions occurring, for example, at the lungs. So let's say that I am at the lungs. What we know that happens at the lungs is you'll notice that oxygen is going into the blood, which is exactly what we want to happen at the lungs, and CO2 is leaving the blood at the lungs, which is exactly what we want because we want to get rid of that CO2. And so now what I'm going to do is show exactly why oxygen is leaving and why oxygen is entering the blood and why CO2 is leaving the blood. So what we know is that we have two things happening. At the blood, oxygen is coming in. We know a little bit of that oxygen can just dissolve in the plasma, a very small portion. Oxygen, though, the primary way it's transported is it diffuses into the red blood cell, and it's going to bind with hemoglobin to make oxygenated or saturated hemoglobin. So this is just that reaction that we saw earlier, where oxygen can bind to hemoglobin to make this. One detail I'm adding right here is that hemoglobin actually usually is bound to a hydrogen atom as well. And when oxygen binds to hemoglobin, that hydrogen atom pops off. So oxygen kind of forces that H plus off. But anyway, it's basically the same reaction. Oxygen binds to hemoglobin to make that, but also it produces this H plus molecule. So anyway, as oxygen levels increase in the blood cell, we know that that's going to make this reaction shift to the right. Because if this increases, we're going to have to try to make more of this in order to balance the reaction out. But here's the thing, if I start making more of this H plus here, actually, sorry, let me go to this reaction first. I'll get to that tease in a second. But now let's look at this reaction of CO2. We know that at the lungs, CO2 is leaving the blood. That means that CO2 levels are decreasing. They are falling. But if this is decreasing, that means that this needs to decrease to balance out. And the way we're going to make this decrease is we're going to make this reaction go to the left. And that's going to keep producing CO2 so that CO2 keeps leaving out into the blood. Out into the lungs. Sorry. I'm making this video too late in the night and my brain is fried. But if some of this doesn't make sense, obviously email me, post below if you'd like, and I'll make sure to get back to you. But basically the idea is that all of these reactions are just following Le Chatelier's principle. CO2 falls, this reaction shifts to the left, and CO2 unbinds from hemoglobin to be released at the lungs. Okay, so we kind of have these two processes happening. Oxygen binds to hemoglobin, CO2 unbinds from hemoglobin. And now let's look at this final reaction. So I was saying earlier, that little teaser is that when oxygen binds to this hemoglobin, this H plus gets produced. But if I start producing more of this H plus, that means that when I think about the other chemical reaction that's also occurring in our blood, that means I'm going to start making more of this here on the right side. But I know that if I have more of this stuff now, what this reaction is going to do is it's going to shift to the left to make more of this to balance out. And that's what we're going to see here in a second. Don't worry about this chloride shift, it's not important for us. But what you notice is that as H plus gets made, increases, this reaction shifts to the left to start producing more CO2. And that CO2 then is going to diffuse out into the alveoli. So we were transporting the CO2 as bicarbonate, but at the lungs, we're going to take that bicarbonate, convert it back to CO2, so that CO2 can now leave into the lungs. Because we can't breathe out bicarbonate, but we can breathe out CO2. You notice that some CO2 also, as we said, is dissolved in the plasma, so that can just leave from the plasma out into the alveoli. So I'll click this to start it all over again. Oxygen comes in. Because of oxygen coming in, that reaction shifts to the right. But also as CO2 levels falls, this reaction shifts to the left. I produced H plus, and that H plus is going to shift this reaction to the left, producing more CO2, and that CO2 is going to diffuse out into the alveoli, the CO2 in the plasma as well. So all of this is going on in your lungs right now to ensure that oxygen is transported by bound to hemoglobin, and CO2 is released from hemoglobin. CO2 is produced so that we get rid of it. Okay, let's look at the exact same thing, but at the tissues. And the idea is that it's the exact same thing, except all the reactions are flipped. CO2 now is coming into the blood. So this is increasing, and this reaction shifts to the right. As a result, we start producing a lot of H plus again. Don't worry about the chloride shift here. But if I produce a lot of this H plus, now it's going to feed into this reaction and cause this reaction to shift to the left. But at the tissues, that's exactly what we want. We want oxygen to unbind from hemoglobin so that it is now free to go into the tissues. Oxygen in the plasma also goes high to low. But now if we look at this last reaction, remember CO2 is coming into the blood. So if CO2 is rising, that means that this reaction is going to shift to the right. And hemoglobin is going to bind to CO2. So all of these reactions are just being set off by the fact that CO2 is rising and oxygen is falling. And that causes these reactions to go right or the left just based on Le Chatelier's principle. So we have all of these reactions going on at the same time. And so just as a quick summary of how we transport all these gases, We saw that oxygen and CO2 can both bind to hemoglobin. They both are transported by hemoglobin. We saw that when hydrogen binds to hemoglobin that already has oxygen, hemoglobin unbinds from oxygen. So another way to say that is that when hydrogen binds to this, so when it becomes that, oxygen pops off. This is what's known as the Bohr effect. Really, all it's saying is that H plus or acidity causes oxygen to unbind from hemoglobin. So lower pH means that oxygen unbinds from hemoglobin. Similarly, so one thing I did not mention, but I'll mention it here, is that oxygen and CO2 actually compete for hemoglobin, so that when oxygen binds to hemoglobin, that actually causes CO2 to unbind. You can kind of think that hemoglobin only likes having one partner. It either wants oxygen or hemoglobin, it never binds to both. So that's another reason when oxygen binds to hemoglobin, CO2 is going to unbind because they kind of compete for that hemoglobin's attention. And this is what's known as the Haldane effect, that oxygen and CO2 compete for hemoglobin binding. Finally, we also saw that CO2 reacts with water to form H plus and bicarbonate, and that's the primary way that CO2 is transported. Cool, so what I would do is try reviewing these reactions in this video and making sure that you understand exactly why each of these reactions is going to the right or the left. And if you have any questions, feel free to email me, post a discussion, or post to the comments below. Most boring YouTube comment section ever, but I love it, so feel free to post and I will get back to you. Alright guys, I'll shut up. Have a great week, have a great night, have a great day. See y'all soon.